Welcome. Today we shall discuss the interaction of radiation with a system that has two energy levels, and we label these two energy levels as 1 and 2. And if my system undergoes a transition from 2 to 1, then the energy difference is comes out in the form of radiation at a frequency. So, this energy difference E nu naught. So, the radiation as a result of such a transition comes out at a frequency nu naught. So, you could think of this as an atomic transition. So, the electron, one of them, this could be the ground state of the electron, this could be an excited state, and this could be the transition between these two. And we shall denote the number density of particles of atoms or whatever systems in the ground state using N1, and the number density of particles in the excited state using N2. Now, we have different mechanisms by which the system can go from here to here or back. So, if I take the system and have some of the particles in the excited state, there is a probability that they will each come down to the ground state, and the rate at which this comes down is governed by a coefficient a rate coefficient a to 1. This is the rate of spontaneous emission. And this is a dimension of 1 by time, and it is the order of the 1 by lifetime of this the excited state. And so if I have a number density of particles in the excited state as N2, then the rate at which it comes down to the ground state is A21 into N2, and this is equal to minus N2 dot, which is also equal to N1, the rate at which the number density of particles in this state goes up. So, this is the first process that could occur, that is spontaneous emission of radiation by de-excitation from the excited state to the ground state. Now, in the presence of incident radiation, so if there is some external radiation incident on this system, this could also then cause the system to go from the ground state to the excited state. And this is so this is the excitation of the system, and this is given by what is called a B coefficient. And the B coefficient tells us that if there is radiation incident on this with this frequency nu naught, so this is the, for any frequency or say it is obviously the frequency around nu naught, which is going, the frequency nu naught which is going to cause this excitation. So, if there is radiation incident on this with angle averaged specific intensity, so J is the specific intensity, the brightness of the radiation averaged over all angles. So, we are assuming that this excitation can be brought about by radiation coming in any direction on this. So, the angle averaged specific intensity into the number density of particles in the ground state into B 2 1 B 1 2. This is the rate at which the particles in the presence of an external radiation field, the particles go from the ground state to the excited state. So, this is going to be minus n2 dot. So, we have these two processes, and these two coefficients A and B are referred to as Einstein coefficients. These are called Einstein coefficients. And in equilibrium, so suppose this radiation, there is an external radiation, and we have some atoms which have, and we are looking at one excited state of the atom and the ground state. So, we want this to be in equilibrium. So, at equilibrium, the rate at which the excitations occur due to the external radiation should be balanced by the spontaneous emission. So, this is the requirement. Now, typically the absorption will occur in a spread of frequencies around nu naught. So, the line has a profile. So, there is something called a line profile. So, typically my atom or my system will absorb radiation in some spread of frequencies around nu naught, where nu naught is the characteristic frequency of this transition, and this spread of frequencies is what I have shown over here. There will be a finite spread of frequencies in which radiation will be absorbed. There will also be a finite spread of frequencies in which the radiation, when this spontaneous emission occurs, is emitted, and this is called the width of the transition. And the natural broadening, natural width of this transition is of the order, the width is of the order of 1 by the lifetime of this two state system. And we have something called the line profile function, which is defined so that it is the fraction of the energy that comes out in each of these frequency intervals, and it is defined in such a way so that this integral is equal to 1. So, when you have radiation of different frequencies impinging on this system, then we have to actually look at the average of the specific intensity, not only over angles, but also over frequencies at the frequency nu naught, and this is j nu phi nu. We do not need this anymore, d nu. So, it is the average specific intensity, angle average specific intensity, also averaged over the line profile. So, the maximum contribution comes at exactly nu naught, but the radiation at other frequencies also can contribute to the excitation of the system, and that whole average has gone into this j bar. So, we should actually replace j bar over here, and that is the rate at which the system gets excited to the there are transitions to the excited state. So, if you consider a situation like this, where now another input that we need is in equilibrium the so let us see, we have a black body cavity, let us say, and there is this black body radiation, inside this black body cavity, and we have these atoms also, these two state systems also inside this cavity, and we wait till they are in thermal equilibrium. Now, we know from thermodynamics, from statistical considered mechanics, that a two state system like this, if it is in thermal equilibrium at a temperature T, then N2 by N1 is going to be equal to G2 by G1 exponential minus h nu by kT. This is the Boltzmann factor. So, this is known from statistical mechanics that if you have a two level system at a in equilibrium at temperature T, then the ratio of the number of particles in the excited state to the ground state will be given by G2 by G1 exponential minus the energy difference by kT, where G2 and G1 are the degeneracies of these two levels. So, there may be more than one quantum state that corresponds to the ground state, that is quantified by G1. Similarly, there may be more than one quantum state that has the same energy level as the excited state. All of them correspond to the excited state, and the number is given by G2. This is what is called the degeneracy. So, this gives me the number of number density, or the ratio of the number densities in these two states. Now, in equilibrium, we know that this ratio should be given by this. Further, in equilibrium, we also expect that the rate at which the absorption takes place should also be equal to the rate at which the emission takes place. So, it tells us that in equilibrium, the emission, the spontaneous emission rate, which is A21 into N2, that is the rate at which you have the spontaneous emission, the particles go from 2 to 1, should be equal to B J bar B12 into N1. So, this tells us that J bar should be equal to A21 by B12, and then we have the ratio N2 by N1, which in equilibrium we know is equal to G2 by G1 exponential minus h nu by kT. But we know that this is so that the black body radiation has a J bar. So, the frequency that we are looking at is somewhere centered at nu naught, and at that frequency we know that the black body radiation J is equal to now obviously you cannot have this equal to this, because these Einstein coefficients just depend on the atom, they are not functions of temperature, neither are these functions of temperature. So, the temperature dependence of this and the temperature dependence of this are quite different. So, you cannot have this equal to this. So, there is some difficulty over here. So, you cannot, if you have just these two processes, you cannot have the system coming to equilibrium, it is not possible. So, it was Einstein who noticed this and who resolved this problem. What Einstein did was Einstein postulated that there should be another process, and this process is stimulated emission. So, in addition to spontaneous emission, you also have, if you have another process called stimulated emission, if you have another process called stimulated emission, it is then possible to have a consistent picture where the system can be in equilibrium. So, what is this stimulated emission? So, the stimulated emission is as follows. When I have a system like this two level system, and there is some radiation incident on it, we assume that the radiation will induce particles to get excited. Now, in addition to this, we have to also admit the possibility that radiation can also cause the system to de-excite, can also cause the system to de-excite, and this is what is referred to as a stimulated emission. So, now if you take into account stimulated emission as well, the rate at which you have the particles going from the, in the absence of any radiation whatsoever, the rate at which the de-excitation occurs, that is the spontaneous emission, is N2 A21, and in the presence of external radiation, it can cause the transition to the excited state, from the ground state to the excited state, and that is given by J bar, that is the average brightness, into N1 B12, that is the rate at which you have the excitations. And what Einstein proposed is you should also include a possibility that the incident radiation will also cause some de-excitation, and the rate of that is given by J bar, that mean specific brightness, into the number density of particles in the excited state, into another Einstein coefficient B21. Now, if you include for this stimulated emission process, so the B21 is the Einstein coefficient that tells us the rate at which stimulated emission occurs. The information that this equation does not tell us is that the stimulated emission is in the same phase as the incident radiation, and this is a very important property. So, the stimulated photon that is emitted as a consequence of this incident radiation is in the same phase and at the same phase and frequency as the incident photon. This is a very important property which we shall briefly discuss towards the end of this class later on. Now, if you allow for this possibility, then in equilibrium we have J bar is equal to so I am dividing throughout by N2. So, if I divide throughout by N2, this will not be there, N2 into B21. So, I will have this ratio B21 in the numerator. So, I am dividing this whole equation by this term, and then I am going to take this term onto the left hand side. So, I have J bar is equal to A21 divided by B21, N2 cancels out, and then I have over here B12 by B21 into N1 by N2 minus 1. We should also compare this with the Planck spectrum. So, in equilibrium we expect this to be the Planck spectrum. So, let us compare it. If we compare it with the Planck spectrum, then we have 2h nu cube by c square and in equilibrium the ratio of these particles n1 by n2 is given by n1 by n2 is g1 by g2 exponential h nu by kT. So, now you see if you put this in here, it is these two can be the same provided these coefficients, Einstein coefficients, satisfy certain conditions. So, let me write down these conditions provided A21 is equal to 2h nu cube by c square B21 and we would like B12 into G1 to be equal to B21 into G2, then all that you have left over here is exponential h nu by kT. So, what we see is that thermal equilibrium is possible provided you have one more process allowed, that is stimulated emission, and further the different Einstein coefficients are not independent, they are related through the relations given over here. Any one of them is adequate to determine all three of them. Okay. And you cannot determine these values of A's and B's from these classical consideration, you can determine them only from quantum mechanics, and these values can be determined through quantum mechanics. Now, so the method that was used over here is a very important technique. What we learned from this technique is called that of microscope detailed balance. So, this technique that we use is called the method of detailed balance. So, what does it do? It assumes that in thermal equilibrium various processes have to be balanced. The rate at which excitation occurs has to be balanced by the rate at which de-excitation occurs. So, in thermal equilibrium if we determine certain relations between the coefficients that determine these rates, and these coefficients we believe depend only on the properties of the system, they have nothing to do with thermodynamics. So, if you can determine certain relations between these coefficients in thermal equilibrium, we expect these relations to hold in any general situation, because these coefficients themselves have nothing to do with thermodynamic equilibrium, right. So, for example, here the Einstein coefficients depend on the properties of my system. The requirement that my two-level system can come to equilibrium with black body radiation tells us that there has to be another process called called stimulated emission, and the different Einstein coefficients have to be related like this. All the three processes have to be related like this. Okay. So, this is something very useful and very new that Einstein discovered, the fact that you can have stimulated emission. Let us now look at the radiative. Okay, let us first calculate what the emission and the absorption coefficients are. So, for these in terms of these Einstein coefficients. So, the system that we are dealing with, we have a medium over here, and this medium is made up of two level systems, could be atoms. So, we could have a medium say gas filling up this region or something like that, any two level system which is described in terms of these Einstein coefficients. Now, we would like to determine the emission coefficient and the absorption coefficient which we have defined earlier for radiative transfer in terms of these Einstein coefficients. So, let us first look at the emission coefficient J nu. So, let us ask the question, how much energy is emitted per second per unit volume in the frequency interval d nu in the solid angle interval d omega, that is J nu, the emission coefficient. And we saw that if you have a number density N2, then the rate at which the spontaneous emission occurs is N2 into A21, and the energy carried in each emission is H nu naught, and this energy gets distributed over different frequencies as phi nu, and it gets distributed uniformly over solid angle 4 pi. So, this is the emission coefficient in terms of the Einstein coefficient, right. Since the stimulated emission depends on the incident radiation, we shall club it together with the absorption process instead of treating it as part of the emission process. The emission is independent of the spontaneous emission, is independent of the incident radiation, which is also the property of the emission coefficient. So, let us look at now the absorption coefficient. So, here again the number density of particles in the if it is in the ground state is N1. So, the rate at which we have the excitations to the excited state, the excitations here, the rate at which energy is absorbed or the number of transitions that occur per unit second is this into B12 minus B21 into N2 this into, now let us assume that the specific intensity that is incident I nu is the same from all directions. Let us assume that the specific intensity, that is I nu, is incident from the same from all directions. So, then J is the same as I, J is the angle average specific intensity, J is the same as I. So, we can write this as I nu, and the energy that is absorbed in each such transition is H nu naught, and the fraction that is absorbed in the frequency interval nu of d nu around nu is to put in the factor of phi nu, and this is what gets absorbed from 4 pi steradian from all directions. So, I have to divide it by a factor of 4 pi to take into account the absorption from a particular ray. So, this from here you can identify that the absorption coefficient is essentially this. So, we have the absorption coefficient and the emission coefficients in terms of the Einstein coefficient. Now, let us next write down the radiative transfer equation in terms of these. So, the radiative let us just in general, the radiative transfer equation is d I nu d tau is equal to minus I nu plus S, where S nu is the source function, tau is the length into the absorption coefficient which we have already calculated. The thing that remains to be calculated is this source function, which let us look at the source function next for this two level system. The source function is the ratio of the emission coefficient to the absorption coefficient. That ratio you can calculate, we can identify from this, and it is equal to again let us divide everything by N2 into B21. So, that is the number density of particles in the excited state into the Einstein coefficient for stimulated emission. If I do that, then in the numerator I have the ratio A21 by B21, which we have seen that this ratio is 2 h nu cube by c square. So, this is equal to 2 h nu cube by c square into what remains is N1 by N2 into B12 by B21, and B12 by B21 is G2 by G1, the ratio of the degeneracies. So, that is my source function. So, let us look at the radiative transfer equation. So, the radiative transfer equation is given over here, and the important thing over here is the source function. Now, there are two possible situations that we could have. The first one is thermal emission in thermal emission. The ratio, the two levels that we are dealing with are in thermal equilibrium, and we have seen that when the two levels are in thermal equilibrium, N1 by N2 is equal to G1 by G2 exponential h nu by kT. So, in thermal equilibrium, this is some material, some atoms, let us say, containing some atoms which, and we are interested in two levels of this atom. So, if this is in thermal equilibrium at a temperature T, then the ratio N1 by N2 is given by this, and the source function is then the Planck function, corresponding to the temperature of the medium. Okay. So, in thermal, if you have thermal equilibrium, thermal emission, then the source function that occurs over here is the Planck function, and given sufficient optical depth, the radiation reaches the Planck function itself. If you do not have adequate optical depth, then it is some other value which is somewhere in between this incident specific brightness and the Planck function. Now, the second possibility is non-thermal emission. Here, this refers to any situation where N1 by N2 is not equal to G1 by G2 exponential, it does not have the Boltzmann form. And there are a large variety of situations where you can have populations 2 levels which are out of thermal equilibrium. There are a variety of populations. A specific case of this situation which is of particular interest is where you have something called population inversion. Now, in thermal equilibrium, the ratio N1 G2 by N2 G1, this number is always greater than 1. So, in thermal equilibrium, is always greater than 1. It is quite obvious from here, exponential of a positive number is always greater than 1. So, the ratio N1 G2 by N2 G1 is always greater than 1, and if this ratio is greater than 1, the source function is necessarily positive, which means that the absorption is in excess of the stimulated emission. When I have some incident radiation, the absorption of that radiation occurs at a rate faster than the radiation is able to stimulate emission, and the source function is positive, and you have the normal situation in these materials. This is called a normal population. And you could, in a variety of non-thermal situations also, non-thermal emission where this does not hold, in a variety, in a large number of such situations also, you typically have this condition being satisfied. So, the population is said to be normal. But there are situations where you have what is called an inverted population. In the situation where the population is inverted, you have N1 G2 by N2 G1 less than 1. Essentially, in thermal equilibrium, the lower energy state is has a larger population than the upper energy state. So, there are more particles in thermal equilibrium, or in typical non-thermal situations also, there are more particles in the lower energy state, less in the upper energy state. So, if you have incident radiation, the absorption where particles go from here to here is more, the emission is less, and the net effect is that the system, the 2-level system, takes radiation, absorbs radiation from the incident, from energy from the incident radiation, or it is in equilibrium with the incident radiation. But when you have population inversion, so population inversion is the situation where there are more particles in the excited state, less in the ground state, and if I put in some radiation, then the stimulated emission exceeds the absorption. And in this situation, the absorption coefficient and the source function, both of them become negative. So, in such a situation, the absorption coefficient alpha and the source function becomes negative, and the absorption coefficient also becomes negative. So, the absorption coefficient becomes negative. This term exceeds this term, and my absorption coefficient becomes negative. So, my optical depth actually decreases as I go further and further along my system. And we know that if I have, this is called an inverted population, here alpha is less than 0 and we know that this is my medium, this is some radiation incident on the medium. We know that inside the brightness falls off as e to the power minus tau. But if it so happens that alpha is negative, then the optical depth actually is negative inside, tau is negative inside. So, you have an amplification of the radiation inside this medium, and it is this which is called maser or laser. So, this is microwave amplification by stimulated emission of radiation or light amplification by the stimulated emission of radiation, depends on which wavelength the whole thing is occurring. So, the net effect over here is that whatever incident radiation that you have gets amplified when it goes through the medium. So, if you have population inversion, then the whatever radiation you have incident on that gets amplified when it goes through the medium. And the fact that the photons that are emitted are in the same phase and have the same frequency is also very important, because then you have an extremely coherent radiation that comes out. So, this is the basic the whole of lasers are essentially based on this extra thing that Einstein introduced, the possibility of stimulated emission, which is found to occur in nature. And there are astrophysical situations where you have inverted populations and you find substantial amounts of masing or lasing activity. Okay. In terrestrial situations, the lasers that we have, you require a cavity and the light is made to traverse the cavity a large number of times, so that you can have a substantial amount of amplification. But in astrophysical situations, the length scales are so large that a single traversal can produce a substantial amount of amplification. Okay. So, this is as far as we are going to discuss about these Einstein coefficients and some very important applications. So, if you are going to discuss the propagation of the interaction of radiation with atoms or molecules, where there are specific frequencies at which transition occurs, in all these situations you have to apply the Einstein coefficients. The Einstein coefficients, one of them will be known, and you with that known value you can calculate the rest of the properties like the absorption coefficient, the emission coefficient, and there are various possibilities that could then occur in such a medium. And we shall go into the details as we go along this course, various applications. Now, for the rest of today's class, I am going to discuss two problems in radiative transfer. The first problem, so let me discuss now two problems. So, we are going to discuss problem number 1. The first problem is as follows. We have a luminous source of mass m and luminosity L, and we would like to determine what is the condition that a gas cloud, let us say the gas cloud has mass small m. So, there is a gas cloud over here, and we would like to determine the condition that the radiation force due to the light coming out from this is sufficient to eject. We want the gas cloud to be ejected. So, we would like to calculate the condition that the radiation force is adequate to eject this gas cloud, and the information. So, the gas cloud that we require is that the material of the gas cloud over here has mass absorption coefficient kappa. Now, I have not introduced the mass absorption coefficient earlier. We have introduced the volume absorption coefficient alpha, which tells us the radiation, that is the fraction of the incident radiation, that is energy that is absorbed per unit volume. Here we shall work in terms of the mass absorption coefficient. So, that tells us the same thing per unit mass. So, let us now see what is the energy that, okay. So, let us calculate the radiation, we have to calculate the radiation force exerted by this massive object, luminous object, on this gas cloud. So, the question is, how do we calculate the radiation force on this? So, let me outline how to proceed. Let us first calculate the energy flux at the location of the cloud. Let us assume the cloud is a distance r away. So, let us calculate the flux, the radiation flux over here. The radiation flux is going to be L by 4 pi r square. That is the amount of radiation energy incident on this gas cloud from this luminous object. Now, let us ask the question, what is the energy absorbed by this gas cloud per unit time? So, that is the energy absorbed So, not all of this energy is going to be absorbed, it is this flux L by 4 pi r square into the mass absorption coefficient kappa into m, the mass of this gas cloud, which is going to be absorbed per unit time. And we know that that is the energy, the momentum rate, the rate at which momentum is absorbed by this. So, we have to divide this by c, and this will give us the force, because that is the rate at which momentum is absorbed, and the rate of transfer of momentum is the force. So, we have calculated the total force exerted by the radiation on this gas cloud. Let us now use this to calculate in the equation of motion of this gas cloud. The equation of motion of this gas cloud is m d square r dt square is equal to, so there is an outward force, and the outward force is L by 4 pi r square c kappa m. There is also an inward force, which is the gravitational attraction due to this massive object, and that inward force is minus g capital M by small m r square. So, the condition for ejection is that the outward force should exceed the inward force. So, let us find that condition. We can find that condition by just equating these two, and the luminosity should exceed some value, so that this term always is in excess of this term. So, the factor of r square cancels out, and the mass of the gas cloud also cancels out, and we are led to the condition that L should exceed, let us see what it should exceed. It should exceed 4 pi into g into the mass of this gravitating object divided by kappa. right. So, this is the value of the luminosity. If the luminosity is in excess of this value, the radiation coming out from this big mass can in principle eject such a gas cloud. This consideration gives rise to a very important concept, the concept being called the Eddington. The concept was first introduced by Eddington, famous astrophysicist Eddington. It is called the Eddington luminosity. The consideration here is quite simple. Suppose we consider a massive object like this, and let us assume that the massive object is made up of hydrogen, and the hydrogen is ionized. There is a lower limit to the mass absorption coefficient that comes from Thomson scattering. So, any charged particle is going to scatter radiation through Thomson scattering, and the cross section of Thomson scattering is sigma t, and this has a value. The value is known. The value is 6.65 into 10 to the power minus 29 meter square. So, that is the for an individual hydrogen atom, the electron essentially is what does the Thomson scattering. It has a value given over here, it is in meter square, and so this is for an individual atom. So, the absorption coefficient per unit mass is going to be kappa is equal to sigma t, the Thomson scattering cross section, by the mass of one hydrogen atom. That is a lower limit to the value of kappa mass absorption coefficient that you can have. It can be more, there could be other processes, it could be more than that, but this much is going to be there. So, now we have a lower limit to the mass absorption coefficient. Now, suppose I have an object of a certain mass and it is extremely luminous, and if it is so luminous, the possibility may occur where it is so luminous that luminosity is adequate to blow off a part of the gas that makes up the object. So, then the object would become unstable, and this upper limit to the luminosity is called the Eddington luminosity. So, if an object of mass m has a luminosity more than the Eddington luminosity, the radiation will disrupt the object, it will force out, it will push out parts of that object, and the object will get disrupted. So, this is the upper limit to the luminosity of an object of mass m, and you can easily estimate what the value of this is by just putting in this Thomson scattering cross section and assuming it is hydrogen atom, the mass of a hydrogen atom. So, I leave it to you as an exercise to calculate the Eddington luminosity. What you have to do is you have to just put in this here. So, what you have is Eddington luminosity is 4 pi g m, the mass of one hydrogen atom MH, divided by the Thomson scattering. And I request you to calculate the Eddington luminosity for a solar mass object, the mass of the sun. We have discussed what the mass of the sun is. Okay. So, this is the first problem that we shall discuss other problems in radiative transfer as we go along the rest of the course.